Hi everyone, good morning, good afternoon, wherever you are. My name is Vass-Varnai. I'm a technical manager at Siemens, and my background is thermal testing of semiconductor components. I've been doing this for approximately 15 years, and I'm actually from Hungary originally. I graduated at the Budapest University of Technology and Economics, and I'm only here in the United States for the last 3.5 years. I'm based in Chicago, Illinois. Very excited to be here with you today. The paper I would like to present is about the measurement of the performance of thermal interface materials in an in-situ test environment. So it will be about measurement techniques, how to evaluate the actual performance, and also how to select different team materials. My co-author is Jimmy He, who is my colleague at Siemens, and also I'd like to acknowledge Laird DuPont Corporation, which provided some of the materials shown in this study. So let me just start and a little bit talk about the challenge when it comes to testing. So one of the most critical things when we try to understand the thermal performance of components is actually understanding the semiconductor's junction temperature, because as the temperature goes higher, what I was trying to say is that one of the most critical things when it comes to semiconductor cooling is making sure that we understand exactly what the junction temperature is, meaning the surface temperature of the semiconductor chip. Because as it increases, the lifetime decreases exponentially, or the reliability or the quality of that thermal system. So proper cooling is very, very important. And for that, component makers come up with different thermal metrics, junction to NVN, junction to case. But for us, system designers, it's actually very often important to even understand the properties of the different layers of that semiconductor package, and also the thermal performance in terms of typically thermal resistance and thermal capacitance, also outside of the package, such as understanding the contribution of the pin. Very often, these measurements are conducted using either thermocouples or infrared cameras, which are very accessible to and very common. The only issue potentially is they are hard to use for junction temperature measurements. So if you want to measure the semiconductor itself, you need to either semiconductor chip or decap the component. Is these traditional methods, they don't really give you the junction temperature. And when it comes to any mathematical model, to understand reliability or lifetime junction temperature is critical. So the other reason we would like to capture the junction temperature is to be able to calculate important package metrics like thermal resistance of different layers within that package, and also the thermal capacitance of those layers. When it comes to transient thermal characterization, it's very important to understand these two values. And by being able to get these values for every single layer, we can actually create very decent thermal model, which you can use for your design or for your evaluation. In order to do this more efficiently, so instead of using thermocouples, infrared cameras, one of the options is actually to take the semiconductor component and use its electrical parameters, such as forward voltage of a diode, collector emitter voltage or gate emitter voltage of a transistor, and use its change as a function of the temperature as a thermal measurement tool. So in order to do this, we need to measure the correlation between device voltage. For example, if I have an LED, I have a steady current going through that LED, change the ambient temperature, I can measure how with increasing temperatures the voltage drops. Typically, it's a fairly linear relationship. And I can do this by putting my component into a temperature-controlled environment, providing current, and measuring the voltage. The whole point about this is it turns the semiconductor chip, semiconductor die inside the package into a built-in temperature sensor. So besides just understanding the temperature, we can actually do more. We would like to get those thermal resistance, thermal capacitance information. So what we can do is use high electrical current to power up the component, make it hot, and turn it off minimum to a very low level and capture the transient response of the. So what you see here is the voltage response of a component as we step change in the power. First, the voltage drops as we go from high current to low current. Then you can see that at this steady current, the voltage increases, and that is because the device is cooled down. So this gives us the ability to measure the thermal impedance curve, the temperature change of the component as a response to this power step. The reason this is important is we can do a mathematical conversion, and by analyzing the temperature transient curve, we can break it down to an RC network model, thermal impedance model, which actually becomes both a structural and behavior model of our thermal system, of the unknown package and the cooling environment of the package. So again, out of this single transient response, we have the mathematical means. We do this using inverse convolution to capture those thermal resistances and thermal capacitances which make our thermal system. And if we plot these values, we can derive 200-300 individual RC elements. If I plot the capacitances as they increase, going away and away further from the semiconductor junction, as a function of the resistances, again, as they increase, as we go further away from the junction, we can see the thermal resistance, thermal capacitance ratio of the individual layers. And we can use that to deduct important structural information of the package. So let me just jump through this and show you a real example how this can be applied for thermal interface material measurements. Of course, if your thermal interface material is not applied properly, as you can see it in these simulations, you're actually reducing the area for the heat flux to go from one layer to another, increasing the thermal resistance significantly. So here's a case study which we created. It was a collaboration with Laird Corporation, today DuPont, and also Toshiba. They provided this board. And you can see the board has 6 power MOSFETs. We indicated them with red rectangles. These actually are motor arrangement. If you do any sort of vehicle electrification, you have the same problem with more high power transistors. And what we did was capturing the thermal performance of different types of materials, high-end thin materials, all the way to less thermally conductive, but maybe more robust materials in terms of lifetime and reliability. The way the measurement was done, so these components were MOSFETs. The way we can measure the MOSFET is that it has a built-in reverse body diode, can send a measurement current through. It's a constant current. Voltage drop will be temperature sensitive. Then we have what we call a driving current that heats up the component. We used different currents and different solutions. If I didn't use any thin material, just air cooling, the maximum we could do was 2 amps, but with more high-end thin materials, we could go up to 20 amps. So way more current, way more power dissipated, yet we could keep the semiconductor cool. Briefly about the arrangement, because we were cooling the component into heatsink, place the thin material between the components and the heatsink. We used the Kapton tape just to do the electrical insulation. We applied the thin between the cooling surface of the MOSFETs and the heatsink here using constant 30 psi pressure, each of the experiments we are going to see. So here is a summary table before I go to the different material types briefly. What you can see is the cooling effect. It's kind of normalized, and even though it's cooling, you see an increasing curve. We flipped it. That's how typically these curves are shown. Sure. The vertical axis is ZTH, it's temperature change over watts, and the horizontal axis is logarithmic time. We can see data starting from 1 microseconds. And what you can observe is if we use air, this thermal impedance goes to the 50 Kelvin per watt range. And with the different themes, we can keep it below 10 or even 5 Kelvin per watts junction to ambient. A couple of interface materials. We've started with high performance phase change materials first. And what you see here is actually this thermal capacitance, thermal resistance map of the entire structure, the way we've resolved it. Initially, you see that we are inside the package. So up to like 1.25 Kelvin per watts, we are inside the package. We drew a line here corresponding capacitance value because we would like to see the effect of the theme right after the package. And for the phase change materials, which are used for like really high power density applications, we could measure 1.2 or 1.3 Kelvin per watts for 2 of the high-end materials. When you do selection, actually it's very important to understand what you're trying to do. For example, if you're trying to cool a processor or a very high power density semiconductor component, need thin bond line thickness, constant pressure, material which softens and flows, then these high performance phase change materials can be an option. Now, tried cure in place materials too, 2-part. What you can know about them is they have less thermal conductivity. So if I look at the same capacitance value, I can read slightly higher thermal resistances. As you can see it here, went to the 1.3, 1.4 Kelvin per watt range. But you can still weigh the benefits. So these kind of materials are very soft when you buy them. They minimize the stress during assembly and they high reliability and shock absorption. So they can be potentially used for some of the space applications too. We have fillers. Same thing, they even have lower conductivity, and actually some of them are even thicker. So overall, if I look at the same capacitance value, I read approximately 2 Kelvin per watts of the resistance. So higher resistance, lower conductivity, but these components, they are high deflection, good pressure versus deflection characteristics, and they reduce vibration and they are easy to use. So again, this shows when you're selecting how to evaluate properties and the actual terms. Of course, if you don't use anything, the thermal performance drops heavily. At the same capacitance using air only, we are at 2.8 per watts, but overall there is a massive jump beyond junction to NVIDIA. I would like to finish with a quick overview table. Basically, depending on the material selection, there are two things you would like to: what power you would like to get to, what corresponding current requirements you have. Here we could go from 2.2 amps all the way to 0.2 amps, keeping the junction temperature maximum fairly constant. They are not exactly the same values, but they are in the same order of magnitude. And in order to be able to get there, if we have better thin materials, obviously we can dissipate much higher power, making our system more efficient. And if we only use air, our power reduced to approximately 10 times smaller than the maximum power we could use with a high performance phase change material. So overall, this is the final slide. And if you have any questions about this study or the measurement technology, I'm very happy to answer.
Yeah, I have one, just a quick one here based on this last slide. But I guess you measure performance in air. Do you have any consideration to testing versus comparison to vacuum? I know that would be applicable for some of these space applications that we're talking about in sometime.
This is a great question. So, if you measure in vacuum, this thermal performance would be probably worse. We can absolutely do that measurement, because all you need to do is to electrically connect to the component, which could be any high-power semiconductor device, anything from a CPU, GPU to a power component. But again, if you only measure in vacuum, probably I would try to use some sort of thin material and cooling solution, and not just rely on radiation, but try to create a highly conductive path from the semiconductor junction to some sort of ambient.
Okay. Yeah, I mean, that's essentially what a lot of these gap fillers are for, right? Just to kind of take up the space so that you have a full conduction path.
Exactly. And what I was trying to show is, when you select, what kind of team you choose, you need to really understand your application. Maybe you really go for the high performance, but then you have low bond line thickness and less shock absorption. But if you use gap fillers, how your performance changes, it drops, but at the same time, it can absorb a lot of vibration or mechanical stress.
All right. Well, it looks like we've got some questions in the chat. Does the high performance phase change materials perform well under ASTM outgassing tests?
This is a question I will need to check with DuPont Corporation. I was honestly focusing on the thermal performance only. I'm not really a team expert, but I'm very happy to ask this and circle back.
Okay. Yeah, no, that's always a concern with any space application is some gap fillers have some outgassing that's involved with it, and you always got to worry about that condensing on other parts of the components. So that's more important, just picking what interface material you want to go with there. We've got another question here. What companies are using this technology, and in what industries?
So this test technology is used mainly in the electronics, semiconductor, also automotive and aerospace industries. Wherever you have semiconductor components which have high power density, it can be anything from an LED transistor for like a high power transistor, a MOSFET or an IGBT for electric traction applications, or maybe a CPU, GPU, any types of VLSI ASIC. And you need to make sure that it's operated in a reliable fashion. Then measuring the thermal performance is extremely helpful. So these are the main industries which we work together with.
Thank you. We got another question in the chat here. What is the difference between the CR and HD materials?
So the HD materials, these are gap fillers. Here is an image, and these are typically those materials you can get in a sheet. You can cut them to the size and shape of your component and easily apply it. HD is high deflection. And the CR materials, they are two-part liquid gap fillers. So these kind of putties which you can dispense with a dispenser, or for an automated manufacturing line.
Okay. Yeah, it just kind of depends on what application you want or what fits, your application best, really.
Exactly. Both of them help you minimize pressure during the assembly, and that can be important, especially in case you're trying to cool high surface advanced semiconductor. You don't want to put too much stress.
Yeah. Okay. We've got another question here. Can the measured data be utilized for improving simulation models?
Yes, so that's another good question. I haven't touched this part, but if you let me just go back here. If you create a simulation of a component, typically you would need to build up the model of that package in terms of physical representation. So you would represent all the different layers with a mechanical model. Need to associate also materials. The second one is typically really. So how do you know the thermal resistance of the paste, or how do you know the thermal performance of the die attach? If you don't have proper data, then being able to measure the real physical device and bring that data over to a simulation model, such as a CFD model, can be extremely helpful, especially when you want to do transient thermal simulations.
Yeah, I can, as someone who's modeled those interfaces before, I can tell you that this data would be pretty useful, if you could, get good measurements of the interface and performance and bring that back in your model. I can see that being a very good application.
Exactly. So it's not just about the bulk conductivity, but you really need to understand the interfacial thermal resistances. And that's something you can get straight out of the measurement.